And here's our next What the Physics video about electricity and magnetism. Specifically, we're going to be talking about magnetism. Oh, wonderful. Yes. So, just like we've been doing a whole lot before, we're going to try to do a comparison, linking it back to what we've already discussed before. That's how we talked about electricity. We linked it back to gravitational. We're going to link some of the magnetism stuff back to electricity. It's always good to be able to review what we learned earlier, hopefully reinforce or get rid of some misconceptions, and it just makes it easier to kind of chunk the ideas together. So, what do we know about magnetism and its similarities to electrostatics? Well, just like with charges, like charges repelling, unlike subtracting, we've got, in this case, poles, north and south poles. Like poles repel, unlike subtract, we have a magnetic field. Now, instead of calling that E for electric field, we call it B for magnet. No, I have no idea why it's B. It just is. Magnetic field is, of course, explaining how we can get magnets to interact with each other, even though they're not actually in contact with each other. Instead of having a plus and minus, we have what's called a north and a south. And just like coming out of the positive and going into the negative, we have them coming out of the north and going around into the south. Okay? And as before, the concentration of magnetic field lines are going to, it's going to help us understand how the magnetic field strength is distributed. So more field lines in a particular area, it's going to be a stronger magnetic field. And the stronger the magnet is, the more field lines there will be. Field lines are not going to be crossing. And this is a little bit peculiar, I guess. They're always coming out of the north and going into the south, but they should always be looping around the whole way through. Okay, so I just drew this to kind of show you, like, oh yeah, it comes out here and goes around there. Really, they should be drawn as full loops going around. Okay, because they don't just go out and die off like electromagnetic fields might. Magnetic fields are always pulled back around. And to understand that, let's talk about some of the differences with electrostatics. Here, it's impossible to get a monopole magnet. Now, what the heck is a monopole magnet? What do we think? It's a, say again, magnet. Okay. Yes, so the magnet with only one sign. Now, it's not, we're not saying positive or negative. Remember, that's electrical. But we'd say a magnet with only north or with only south. That is just not going to happen. You say, oh, that's okay. I'll just take a magnet and judo chop it in half, right? Okay. No, doesn't work out that way. You can break up a magnet all you want. Well, not one of mine, one of yours. Break it up all you want. It's just going to break apart into smaller north-south magnets. You'd have to break it up down to the atomic level, and it's still going to be this way. Why? Well, it comes down to basic concepts with magnetism. Okay, and as we'll see in just a moment, magnetism comes from electric charges moving around. And I don't know if you guys talked about this in chemistry at all, but the fact that the electrons are orbiting the nucleus, they actually give off some magnetic field. Did you ever talk about that in chem? No? Okay, well, that's fine. We get to talk about it here. So, let's see. The unit for magnetic fields, that would be the Tesla. And you say, oh, it's like the car, right? Well, they were both named for the same person, Nikola Tesla. But no, it's not like the car was named after the field or vice versa. Interesting side points. When I was in college, there was this physics major. I think she was a year or so, maybe 2 years ahead of me. Her name was Tesla, and her parents were both physics or physicists, physics majors, something like that. And naming her Tesla, I guess, uh, predetermined that she must go into physics because, why not? And that's a cool name anyhow, Tesla. Uh, she never shortened it to like Tess or La, Tesla. I don't know. Moving on. So, a charge in motion produces magnetic force. That's what we were just talking about. Apparently was not introduced to you in chemistry, but that's okay. An electron can be sitting there and giving off its own electric field, but if it's in motion, it's giving off a magnetic field. Now, with the whole motion thing, we do have to keep in mind that velocity is relative, so the charge has to be moving relative to whatever the background area is. So the charge has to be in motion, and it turns out the faster it's going, the stronger the magnetic field is going to be. There's a few more important things to keep in mind, but that's direction and stuff. But we'll discuss that soon. If the magnetic field, the magnetic force is going to be 0 if the velocity goes down to 0. A cool application of this is what? What is this representing up here, do you think? Hydroelectric dam, yes indeed. Okay, so this is how, some parts of the world, and we do have some hydropower in the United States, not extensively, but we do have some, can get electricity. Whenever I visualize this, I always visualize like a waterfall and like water going over the dam and causing the turbines to spin. It's actually, typically sending it down here, and the water flowing through will cause the turbine to spin. And then we got a generator, and I should talk about that toward the end of these notes, creating electricity. Okay, so in here, we've actually got magnets. Okay, so I said a moving charge will create a magnetic field. It also works the opposite way. A moving magnet will create an electric field. So that's how we're able to create electricity here. And this whole generator and turbine thing is actually how the vast majority of energy source things work, whether it's a coal burning plant or a nuclear energy plant, or most anything uses some type of turbine concept. Solar power does not, but pretty much everything else, natural gas uses this, pretty much everything else uses this to create electricity. When you think of magnets, what do you usually think of? Who's ever played with magnets before? Raise up your hand. Not quite everyone. All right, well, wow, all right. Magnets are fun. Go ask your folks for some magnets or a little play set or something. Most people have magnets stuck to their fridge or something, right? Maybe letters stuck on their fridge, if nothing else. I guess we have them in our house because of offspring, but sometimes they're just fun to play around with. Okay. You put a magnet on the fridge, it sticks. How come? Is the fridge a magnet? The refrigerator itself is not a magnet, but it can become effectively polarized, just like we were talking about with, say, you rub a balloon on your hair and you stick it to the wall and it stays there, right? Same thing here. It's the whole polarization idea. Okay, it's just polarizing one little section of the fridge door. Here's a little mnemonic for helping to remember what a lot of permanent magnets are made up of: the Alnikov, aluminum, nickel, cobalt, such. Now, they're called permanent magnets, or I'm not sure what that V is, Alnico. I don't know why I said that V. Maybe that's a misprint. I don't know. Permanent magnets are a bit of a misnomer. because they're not necessarily permanent. They can lose their magnetic properties, and they can be remagnetized, but it's not like they're this way forever. They are distinguishing permanent magnets from what we'd say as electromagnets. And my guess is you probably dealt with electromagnets in maybe 8th grade or something. What else might you think of? You might think of a compass, right? Who has ever used the field compass before? Raise up your hand. Okay. Okay, not quite everyone, but that's fine. What can you tell us about your use of the field compass? What did you use it for? What were you involved in? Were you hiking? Were you just walking around saying, "Hey, this is a compass. Look at me"? Yes.
Navigation, and like those checkpoint games and
So, okay, so navigation type stuff, and you said checkpoint games like what?
you have a map and a compass and you're looking for like spots to go.
Okay, so yes, using the map and the compass that can help you get on the right path. You say, okay, from this special tree, I'm supposed to go a certain distance north. Well, which way is north? If you're not going in the correct direction, you're not going to end up in the right spot, right? Okay, so I imagine they do a bit of this in like scouts and stuff too, right? Many people are in Boy Scouts or Girl Scouts or whatever, maybe, sure. Yeah, fair, that's what we do. Okay, thanks. All right. They also do this type of thing with geocaching, although actually in that case, they probably wouldn't use magnets, they'd use just GPS devices. But it's the same basic idea, it's telling you where to go. Okay, so how is it that magnets will work? How do field compasses work? This is magnetized here, and this end, it's usually the red end, is the one that's supposed to be pointing north. I guess it depends on the compass. They have different colors. Okay, you can visualize the Earth as having a giant bar magnet inside of it. Does it actually have this inside it? No, it doesn't, and we'll talk about that in a moment. But visualize it like it is. Okay, so there's this giant bar magnet in here. Now, if we take a look at this, notice something that might surprise you. Up in the North Pole, the geographic North Pole, what side of the magnet is actually up there? The south end of the magnet is going to be up there. And you say, well, that's weird. Why would it be like that? Well, because this is the north end of the magnet, and north is going to be attracting to south. So we would still call this magnetic north, but we would realize in terms of physics, it would actually be a south pole up there that would allow attraction to the north. Another interesting thing on there is the magnetic North Pole and the geographic North Pole are not actually in the same spot. Geographic North Pole is, of course, way up at the tippy top where we imagine there's, a giant pole sticking out. Maybe Santa Claus is up there, who knows. The magnetic North Pole is actually somewhere up in northern Canada. So I'm sure that's fun for them, taking ownership of cool stuff. Now, I said there's no way that it's actually going to be a bar magnet stuck in the Earth. The reason for that is because the Earth is way too hot. I had said permanent magnets can depolarize. A common way of doing that is by dropping them, so you always want to be careful with stuff. Dropping it can actually reorient the little domains in the magnet. So you got to be careful with magnets. Another way to screw with it is putting it around a whole bunch of other magnetic fields that can sometimes reorient or at least weaken it. And typically, or at least sometimes seen in the science fair project, is when people try to cook magnets and see if they can get to the Curie point, which is when magnets don't work anymore. And let me just clarify for you, that's got to be really, really super hot, okay? But it's going to be hot enough in the Earth's core to depolarize a magnet. So that's not going to apply here. Okay. We can trace the magnetic field lines, and we'll actually be doing this as an activity later on. We put down a whole bunch of compasses and put down a magnet on top, and we can see these kind of all tracing around. And here are the magnetic field lines, as we said, going out of the north, going into the south. That's lovely with a permanent magnet. This also works with a wire, a current-carrying wire. In this case, we've got a nice visual, and visuals are going to be our friend here. Visuals are very important when it comes to magnetic field lines because it's just gets a little bit crazy here. We have this wire here, yes, and current is traveling up here. And what we can do is we imagine we put down a bunch of field compasses on this little chunk of cardboard, and we'd actually see the north pointing this way, this way, this way over here. Over here, north would point this way, point kind of down this way. And we'd be able to say, oh, well, that's because the magnetic field lines are actually going around in circles around current-carrying wire. And it turns out the closer it is, the stronger it's going to be and such. Now you say, what direction is it going to go in? Well, we'll get to what's called the right-hand rule in a little bit, and we'll see. Okay, a little bit about magnetic field strength. Magnetic field strength goes away as 1 over R. And as I was just saying, the farther away you are, the smaller the magnetic field is going to be. This is different from electric field. Do you remember what the equation for electric field was in terms of distance? Anyone have any recall of what that was? Maybe what I'm pointing at right now on the board. That could be it. I'll give you a hint. It's written in purple, and my finger is pointing at it. Can anyone maybe say what the equation is? E is equal to K times the big Q divided by R squared. The important part about that, at least what I'm discussing right now, is the over R squared. Magnetic is just over R. So you say, oh, wow, fair. That sounds really exciting. Well, okay, maybe you're being sarcastic right now. But it's actually pretty cool. Why is there this difference? I've not actually found any type of explanation on why. When I look through textbooks and stuff like that, I don't get anything. However, I'm kind of curious. Maybe it's the fact that electric field lines from a charge are going off radially in all directions, right? I've got this point here, and they're moving out up, moving out to the right, moving out to the left, moving down, forward, all these things, right? Going out like a sphere, or more appropriately, like the shell of a sphere. What's the formula for the surface area of a sphere? Starts with a 4. Yes, 4 times pi r squared. Okay? So there's that, but then we can also visualize for a magnetic field. So in this case, the charge is moving along the wire. So it's not radiating outwards in all different directions. It's just radiating outwards as a circle. What's the equation for the circumference of a circle? 2 pi r. Just plain r, not r squared. Okay? So I'm not sure if that has anything to do with it. That was just one of those thoughts that I had, way back when. I'm like, And no one has ever been able to clarify for me, like, that's exactly it, Fair, you're amazing. Kind of like what I was saying earlier on in the year with the whole, it's like, oh, look, the derivative of this is that. Oh. And people are like, yeah, we know. So far, no one has beaten me to the punch, so there. Another important thing about magnetic field strength is it's proportional to I. So the larger the current is going to be, the stronger the magnetic field is going to be. Put all these together. I mean, you got an equation, but I don't really care. Blah, blah, blah. End result. Magnetic field is proportional to current. Magnetic field is inversely proportional to R. Okay, so you want to pick up a whole bunch. If you want to make, say, an electromagnet, and you want to wrap a wire around the nail, you've probably done this activity before, yes? We don't have nails at my house. They're not allowed. No one has ever done anything like this before. Wrapped a wire around a nail and had... huh. Okay, yes, thank you. All right. Yes, picked up some paper clips with it, right? Or picked up whatever. Okay? You say, oh, look, I have this much current going through. I can pick up 2 paper clips. I have more current going through. Now I can pick up 5 paper clips, 10 paper clips, and so on, right? Okay, that's what we're talking about. Let's talk about magnetic field direction. Let's talk about this thing called the right-hand rule. And you guys will need to practice this because this is kind of confusing. Okay, as we said, a current-carrying wire is going to give off a magnetic field. So you imagine a charge running down this wire. It's giving off a magnetic field, but it's going out perpendicular to the wire. Okay, and that whole perpendicular thing is super duper important. If we're looking at it from, if we're looking at the magnetic field going directly outwards from the wire perpendicularly, that's going to have the strongest field. It goes along with this whole sine theta business, if you recall using that from earlier parts of the year. Okay, if it's perpendicular, that's when it's the strongest. If it's parallel, that's when it's 0, the weakest, right? Yeah, okay, good. Speaking of directions, we can use right and left and up and down. But then when we're talking about in and out of something, we have to be able to draw that pretty well. Who has ever thrown like darts before or shot an arrow before? Okay, most people. All right, good stuff. More people have shot arrows than played with magnets. I don't know. You throw a dart. What is the last thing of the dart that you see as it's going away from you? The tail ends, which looks like a what? Little X, right? Okay, so that's actually how we represent stuff when it is going away from us. And by stuff, I mean it can be force, it can be current, it can be magnetic field. We'd usually label it. But if we want to say it's going away from us, or like into the board, so going into the board would be going away from me. Okay, I draw it as that X. If you were unlucky enough to be involved in a dart game or launching arrows, and you happen to have one of these darts or arrows coming right at your face, hopefully you were wearing safety goggles, maybe a lab coat, what is it that you would see? You'd just see the tip of it. You'd see a point coming right at you. So if it's coming like out of the board toward your face, it would be shown as this dot right here. Okay? All right. So now that we understand this directional thing, we got to use these things because drawing three-dimensional fields and forces and stuff on a two-dimensional surface is very difficult for most people. Okay? To demonstrate this, we're going to use the right-hand rule, the RHR. So everyone get out their right hands. Everyone bring their right hands today? You forgot yours? Raise your hand if you... No, see? No, okay. Mr. Fair, I'm raising my hand because I forgot my hand. No, okay. And you also want to get out a pencil. Or a pen. We'll assume the pointed end of the pencil or pen is the direction that current is flowing. And we're going to use our thumb to go along with the direction of current. So get out your right hand, open up your hand, lay the pointy end of the pencil to go parallel with the direction your thumb is pointing. And then wrap your fingers around the pencil. The easy way, not the bone-breaking way. That is showing us the direction of the magnetic field. Okay? If you had the pencil, and now you can adjust the direction of your pencil, right? If you have your pencil pointing like along this direction. If you have it pointing right out in front of you, if you have it pointing to the left, yes? Okay. This here is showing us the direction of the magnetic field. So above the wire, so I'm holding up my pencil, above the wire, which way are my fingers pointing? They're pointing, are they pointing up, down, left, right, in, out? What are they doing? I keep motioning my fingers so that people can reference something. They're pointing into the board, yes? Okay, so my fingers above the wire are pointing into the board, yes? Okay. What about below the wire? Which way would my fingers be pointing? Out of the board, towards you, right? They're coming out of the board. What about this area kind of in, so right up here, it would be pointing into the board. Down here, it would be coming out of the board. What about like this area in front of the wire? On our side of the wire, what is it going to be doing? Pointing which way? Come on, you all have your right hands. Come on. Pointing which way? Which way are my fingertips pointing, please? Upwards, towards the ceiling, yes. Okay, and then behind here, which way is that going to be pointing? That's going to be pointing downwards. Okay? If instead, to just get a different perspective, we put our pencil like this, in this case, it's like the current is coming out of the board, so that means the pencil tip would be facing us. We'd wrap our fingers around like this. Okay, and we could say like clockwise or counterclockwise. In this case, it's counterclockwise. In this case, if the charge were moving away from us, we'd see it's going to be clockwise. Here's perhaps a nicer visual of this. So the charge is going up the wire. We wrap our fingers around. So on this side, the left side of the wire, the magnetic field lines would be coming out of the screen. This side, it would be going into the screen. In front of the wire, it'd be going to our right. Behind the wire, it'd be going to our left. Okay. This is one of the right-hand rules. Sometimes we call it the curled right-hand rule, as in we're wrapping our fingers around this. This is the other curled right-hand rule. It's kind of an extension. It's some physics teachers teach it and some don't. Some don't because they figure it might be too confusing to add in a different one. Okay, but this is that whole wrap a wire around the nail type setup. You do this a whole bunch of times. In fact, you probably notice the more times you wrap the wire around, the more paper clips you can pick up, right? Yes? Okay. What you're doing is you're concentrating the magnetic field into a very, very small area. By squishing all these field lines in together, you're going to have a very large field line density. And we said, oh, large field line density, that means it's going to be a very large magnetic field, right? Yes. Okay, in this diagram, it shows it a little bit easier. I'll refer back to the nail. We'd see that they're all wrapped around, and the north is coming out this way. The south is coming in from this way. You say, wait, Fair, how did you just do that? Okay, you can do it like this, where this is the positive end, and we're always visualizing this as the direction that the positive charge would flow. It's coming along here, it goes behind the nail, and then down in front, behind and down in front, behind, around and around and around. You could pretend to grab hold of one of these wires along here and wrap your fingers around, and your thumb would be pointing down this direction, and you'd be able to get the direction of the magnetic field. You could do it that way, but kind of a shortcut that sometimes we use is we switcheroo the magnetic field and the current. Most all the time, we're going to have our thumb being the current and our fingertips being the magnetic field. But for a solenoid, we can do a little switcheroo. and we just wrap our fingers in the direction of the current flow. So as we saw here, look, the current is going up behind here and down behind here. So my fingers would wrap around, pointing downwards in front of the solenoid. That means my thumb is pointing this away. That's going to be north, yeah? Okay. So this is another version of the curled right hand rule that's specifically for a coiled wire. You don't necessarily need to know this one. You can always use the original version, where our thumb is always going to be the current and our fingertips are always going to be the magnetic field. But it's up to you. Okay. Anywho, that's the curled right hand rule. Then we're going to use the open palm right hand rule. The open palm right hand rule is good for when there's an external magnetic field. So current carrying wire can give off a magnetic field, but it can also be affected by an external one. So that's why I have a picture of Magneto here. Okay, so you imagine you put this wire, this current carrying wire, going through this magnetic field. Well, it's going to create its own magnetic field. The question is how they're going to interact with each other. In some orientations, they might cause motion this way. Some orientations, they might try to push away from each other. Some orientations, they won't even interact with each other. Remember that whole perpendicular thing. Okay? There's two equations for magnetic force, and they're actually very similar to each other. First one is Philb, F equals ILB, where I is the current, L is the length of the wire in the magnetic field, and B is the magnetic field itself. And then, of course, there's the sine theta in there. Everything's got to be perpendicular to get our maximum values. Then we've also got this one, F equals QVB sine theta. Okay, so we've got I, which is current, times L, which is length, or we can have Q, which is charge, times V, which is velocity. If we think about what each of those means, I is the amount of charge going by per time, so it's Q divided by T. And then L is just the length, so that's distance. Well, what have we got down here? There's my charge. What's velocity? What's the equation for velocity, peeps? It's right. Okay, it's distance divided by time, right? So it's really the same equation, same. And as we mentioned, the force is going to be stronger if everything is perpendicular to each other. So the open palm right-hand rule goes like this. Okay, there's this lovely picture showing us. My thumb, once again, is the direction of the current flow. So, no, don't have your arms curled up. Don't have your hand curled. Have it open like this, like you're going to high-five someone. Okay, but your thumb is sticking out perpendicular. Your thumb is the direction of the current. The fingers, that's the direction of the magnetic field. Bless. And then the force is like coming out of the palm of your hand. If you're going to push on something, it's like you're going to push with the palm of your hand, yes? No, don't push on his face. Oh, okay, yeah. Or his shoulder. Let's just not push on each other in general. Okay? He's not a magnetic field. Okay, so this means if I know the direction of the magnetic field, if I know the direction of a wire or a current going through a magnetic field or a charge going through a magnetic field, I can figure out the direction that is going to be pushed on. So the wire can actually be pushed out of the way. A charge running through a magnetic field can actually be caused to go off course. And we'll talk about applications of that in the future, but it's really cool to be able to see all these cool applications. Okay, now it's making sure that we understand this. This, as I said before, is working for positive charge. We're visualizing this as always for positive stuff. So if a proton is moving along. Our thumb is going to be pointing in the direction of the proton's motion. What if it's an electron? Well, then we just pretend it's a proton. We point it in the direction of its motion, and then flip it around at the very end. We say it's opposite day. So if I say, oh, okay, setting it up like this, the force is going to go to upwards. Okay? But wait, it's opposite day because it's a negative charge, so flip it around, the force is now downwards. Okay? What I'd like you to do is try out these example problems. There's several example problems for you to work on, and they're good stuff. This image here is the way I learned it in college. It depends on the textbook. Some do it the open palm. Some people do it like this. Okay? Fun, fun, fun.